Hi, and welcome to Dr. V's AP Chemistry webcast. In this webcast, we're talking about gas stoichiometry. Specifically, we're going to focus on gas stoichiometry problems that are not at standard conditions. Here's what I'd like to accomplish in this webcast. First, I want to review molar volume at STP and review what STP is, and do a stoichiometry problem at standard conditions. And then we'll go on and talk about strategies for doing gas stoichiometry problems when you're not at STP. How do we combine the gas law calculations with the stoichiometry calculations to put it all together and get the answer that we need? And of course, we're going to do practice problems. Would it be a Dr. V webcast if we didn't do some practice problems? One nice way to think about all of this is to go back to Avogadro's hypothesis. This hypothesis states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Kind of goes in the other direction too, which makes it really handy. So for these three gas samples, they all contain 6.02 times 10 to the 23rd particles. They have different masses, but they have the same pressure, and you'll notice they all have the same volume. So they'll have 1 mole of gas and equal volume, and that's really the key to these calculations. So we can derive the molar volume of a gas from Avogadro's hypothesis. 1 mole of a gas at STP occupies 22.4 liters. Now, this is only true for gases, not other states of matter, and it's only true at STP. Well, what is STP? If you've forgotten, let's review. STP stands for standard temperature and pressure, and it means it's 1 atmosphere and 0 degrees Celsius or equivalent units. We can use this to do gas stoichiometry problems at standard conditions. And in fact, let's go right on and do one. Here's a classic gas stoichiometry problem at STP. If 32 liters of oxygen are consumed, according to the reaction above, at STP, how many liters of CO2 will I make? So we're starting with a volume of O2, 32 liters. We want to know how much CO2 would be involved. And we're going to set it up as a dimensional analysis problem. And we are at STP, and that means we can use the molar volume of a gas. So we'll set up our dimensional analysis. I can use 22.4 liters of O2 to get to moles of O2. I can use my mole to mole ratio to get from moles of O2 to moles of CO2. And then I can use the molar volume again to get from moles of CO2 to the volume of CO2. Now what you'll notice, and it should jump right out at you, is that 22.4 liters cancels. Meaning what really affects my answer is the mole to mole ratio. And so my final answer ends up being 19 liters of CO2. I only have 2 sig figs. And if you're curious, this is sometimes referred to as the law of combining gas volumes, the fact that it's really just the mole ratio, the coefficients that matter here. So what do we do when we're at non-standard conditions? If we're not at 0 degrees Celsius and 1 atmosphere of pressure, how does that affect what we do in terms of the math? What we have to remember is that gas volume can change dramatically when the pressure of the gas changes or when the temperature of the system changes. But mole to mole conversions aren't affected by this. And so we can do a gas calculation to account for pressure and temperature changes, but the stoichiometry conversions are not going to be affected, and that's just regular dimensional analysis. So this usually gives us some choice in pathways to proceed through the problems. It does mean that we want to plan out our calculations. So if you're starting the problem because you're given a volume of gas that's not at STP, you can convert it to STP by using the combined gas law, or you can find moles of gas using the ideal gas law. And then you can go on and do your mole to mole calculations and what other stoichiometry calculations are required. If you're going in the opposite direction, if you're solving for the volume of a gas at non-standard conditions, you do all your stoichiometry calculations, mole to mole conversions, and then you can convert your volume to the stated conditions. And again, you have a choice. You can either do that with the ideal gas law or the combined gas law, depending on where you stop and start. Sometimes students find it helpful to have a visual roadmap through these problems, so I actually put one together. If we're starting with a gas volume not at STP, we could use the combined gas law to find the volume of that gas at STP, and then use the molar volume of a gas to find moles of the gas. Alternatively, starting with the gas volume, we could use the ideal gas law to get to moles of the gas. And then we're going to do our stoichiometry calculation to find moles of what we need and to calculate whatever that final answer is, whatever that final value needs to be. So let's do a problem of that type. How many grams of calcium carbonate must react with excess hydrochloric acid to form 46 liters of carbon dioxide at 28.2 degrees Celsius and 0.76 atmospheres? We are given the balanced equation. That's always really helpful to have that. So I'm solving for mass of calcium carbonate. I'm given a gas volume, and notice that I'm not at STP originally, so that's important. So again, I've got a couple of choices. I'm going to go with the ideal gas law because that's what I feel like doing, but you could do it the other way too. You can pause this and work out the problem both ways and compare your work with mine in the end. So the first thing I'm going to do is find moles of CO2. I'm going to use the ideal gas law, like I said. I can rearrange it. I can substitute in my pressure, the initial volume of the CO2, the universal gas constant, noting that I need the pressure units in my R value and the pressure units in the problem to match. And I need to convert my temperature to Kelvin as well. All right, always got to be in Kelvin with these gas law calculations. And from there, I can go ahead and calculate the moles of CO2 gas that started for the reaction. Now that I have that, right, and of course, I really only know that to 2 sig figs. I'm not rounding yet because I don't want to introduce a rounding error, but I know that in the end, I'm only allowed 2 sig figs in my answer. Now that I've got 1.41 moles of gas calculated, I can now do the stoichiometry piece. All right, I've got 1.41 moles of CO2. I want to know how many grams of calcium carbonate would correspond to that. From the balanced equation, I see that they're in a 1-to-1 ratio. The molar mass of calcium carbonate is just over 100 grams per mole. And then I can get my final answer reported to 2 sig figs, 140 grams of calcium carbonate. Now let's talk about a visual path through problems where I'm solving for gas volumes when I'm not at STP. So I'm given enough information to solve for the moles of whatever it is that the problem started with. I can calculate the moles of that, and from there, I can use my mole-to-mole ratio to find the moles of what I'm going to ultimately need for the problem. And then again, I've got 2 divergent paths I can take. I can use the ideal gas law to find the volume of the gas at those reaction conditions, or I can use the molar volume of a gas at STP to find the volume of that gas, what it would be at STP, and then use the combined gas law to get to my final volume. So there's a little extra work here, but it all comes out to the same point in the end. Again, you're going to choose the path that makes sense to you. You want, as long as it's logical and reasonable, that's fine. You're going to get the same answer. So let's go on and do a problem of this type. What volume of carbon dioxide gas measured at 19.8 degrees Celsius and 1.26 atmospheres can be produced by the combustion of 4.7 grams of ethane? I know I've got a whole lot of combustion reactions going on here. That's fine. So, all right, the first thing I'm going to do for this problem, I'm going to find the CO2 volume at STP. Why? Because again, it's all going to work out just fine. Again, you can pause this and do the work on your own and do the other strategy if you want and compare your work to mine. So I have the mass of the ethane. I can convert it to moles of the ethane. I can use my mole-to-mole ratio to find moles of CO2. And then I can use the molar volume of a gas at STP to find the volume of the CO2 at STP. But the problem, right, the conditions that I need are not at STP, so I need to do some additional calculations. So since I have the volume at STP, I can find the CO2 volume at the conditions of the reaction, and I could do this with the combined gas law. All right, so I'm going to set it up and solve for V2. So really what I'm going to do is set it up so that STP is my initial conditions and the second set of conditions are what I'm solving for. So I'm solving for V2 here, all right, and I can substitute everything in, and I get an answer of 6.0 liters. If I did it by solving for the moles of CO2 and then using the ideal gas law, I also get 6.0 liters. So it's very convergent here, right? Which is good. That's what we expect. So let's summarize what we've done here. We can do gas stoichiometry problems at non-STP conditions. These involve a stoichiometry calculation and a gas law calculation. It's all about the sequencing, and you really have to think through that, all right? What part do you need to do first? What part do you need to do second? And plan it out before you start doing the calculations. If you found this video helpful, subscribe to my channel and leave a comment. Have a great day, everybody.